Hello everyone, my name is Jonathan Etumuse and I'm here to present to you the novel Martingale approach for change point detection. This is for the 20th International Conference on Intelligent System Design and Application ISDA 2020. The co-authors are myself, George Martinez Caracedo, and Sally Macklin, all from Ulster University. So we move to the content. We have the introduction, the problem, the previous approaches, the Martingale framework, the proposed approaches, the results, the analysis, the feature work and conclusion, and the references. Then the introduction. In this presentation, we will cover the various challenges of several algorithms for anomaly detection in terrestrial dataset. We also look at some of the related and relevant work and introduce two new methods. What is electromagnetic dataset? Electromagnetic dataset provides critical information about high electrical conductivity and geological structure which are concealed. So the electromagnetic dataset has information that are concealed in it. And through this information, we can analyze and enable researchers to identify anomalies or abnormalities when it comes to geological areas. What is an anomaly? An anomaly is defined as a deviation from what is unusual. An abnormality is something that that is not right with the rest of the structure. We have three types of anomaly. We have the point anomaly, the contextual anomaly, and the collective anomaly. What is anomaly detection? Anomaly detection can be defined as the identification of abnormal pattern that does not conform to normal trends. In mathematics, anomaly detection is the detecting of that variable that is far away from the mean. Anomaly detection can be classified into two parts. We have the supervised anomaly detection and the unsupervised anomaly detection. The supervised anomaly detection detects changes by classification of new data sets that have been labeled, while the unsupervised anomaly detection is a method that can detect changes in a given unlabeled data set. The problem: electromagnetic data set accumulated from terrestrial stores can have potential noise interferences, and this could lead to false identification of change points. A lot of data they have, analyzing electromagnetic or terrestrial data sets has a lot of noise interferences that could really affect anomaly detection. Now, another of the problem is, how do we develop an efficient analytic model that can identify these abnormalities in electromagnetic dataset? This scope can be very, very challenging. We look at previous approaches. The wavelength-based method can identify an abnormality in electromagnetic dataset, but the change measure is low. We also have the geometric moving average method, which can also identify abnormalities in EM dataset. However, the algorithm is limited to noise interferences. We also have the fuzzy-inspired system, which only shows the detection within the boundaries between the standard data and an anomalous sequence in EM dataset, but the algorithm is still limited to noise interferences. Then we move to some challenges. We look at the general challenges of anomaly detection. Complexity in handling terrestrial datasets. Terrestrial datasets contain, as we've mentioned in the previous slide, which is regarded as undesirable. Most algorithms are unable to measure the extent of these changes that takes place in the time series. It is a challenge to differentiate between normal and abnormal boundaries. The characteristics of data differs, which means that anomaly detection that is applied successfully from one data might not be effective for another data. So it depends on the data set and it depends on how it is being implemented. So those are the challenges of anomaly detection. Now we look at the Martingale framework. The building block or the use of Martingale framework known as the randomized power martingale in anomaly introduction was introduced by Ho and Wishler. The RPM is effective. It is a very effective algorithm for identifying changes in data stream. Now we look at our own approach. Our approach is really to improve the randomized martingale. In order to improve this randomized martingale, we'll propose two methods known as the moving median of the martingale sequence and the Gaussian moving average of the martingale sequence. This proposed method can accurately identify abnormalities in electromagnetic datasets, and this is achieved by reducing the effect of noise in the dataset. Now, this is our system flow. We identify data, we analyze this electromagnetic data using machine learning and statistical model, we detect changes, we raise alarm, then to the decision support system and community safety. So basically, our algorithm is basically to identify abnormalities in terrestrial dataset and to send that information to a decision support center for community safety. An example is an earthquake. So we want to look at how effective our algorithm is compared to the previous randomized power martingale. So we look at very frequently used terminology, such as the true negative, true positive, false positive, and false negative. And these metrics are clearly defined as follows. The accuracy, the precision, the recall, and the F1 score are defined in order to evaluate the effectiveness of our algorithm. So from this table, we're able to see that our approach is far more effective than the randomized power martingale. We look at the moving median of the martingale average has 68%, which is 84% true positive rate, which is more effective than the randomized power martingale, which has a 53.3 positive rate. And if we look at the other terminology, we see that our method is more effective than the previous randomized martingale. Now we look at the accuracy and the recall F1. We can see that our algorithm has an effective F1 measure compared to the previous randomized power martingale. The MMMS has the 0.6355 F1 measure, and the GMAS has 0.5392 F1 measure, which is very effective compared to the randomized power martingale, which has a 0.3814 metric. Now the analysis. From the metric result presented in the previous slide, we can also conclude that our proposed algorithm presents a higher true positive detection ratio and a lower false negative detection ratio when compared to the previous RPM. The proposed algorithm presents a higher accuracy F1 compared to the previous RPM. The proposed method ignores most of the false positive detected by the RPM. It shows that how effective our method is. Now we look at future work. Now what we're going to do in the future is expanding this test to include other time series, and we have only tested this algorithm on the electromagnetic dataset. So we want to expand it on other datasets to see how effective this algorithm is. We also need to implement this algorithm on high-dimensional dataset, multivariate dataset, using classification forms such as KNN algorithm to compute the strangeness of the dataset. We're also going to develop this algorithm into an application that will process, analyze time series effectively. And in conclusion, we've said, throughout from the slides, we've concluded that we've introduced two novel Martingale framework has been developed. The initial goal of this project was to improve the accuracy and precision of the current Martingale framework. From the result, we found that both proposed algorithms provide efficient change detection. Is very efficient when it comes to change detection in detecting electromagnetic dataset, in detecting abnormalities in EM dataset, and they can also reduce false positive identified by traditional methods such as the RPM. Both methods output a higher accuracy and information compared to the previous method. And thank you very much again, and God bless. And this is my name and my email address in case you have any question. Thank you for listening. Cheers.